Okay, in this lecture we're going to talk about the tangent space and the concept of velocity. This is actually going to be probably our most difficult lecture because this subject here is not easily grasped, and in the previous versions of my lectures called What is a Tensor, I didn't even try really. If you followed those lectures, what you saw me do is create a coordinate system on a space-time, and I called these coordinates x0 and these coordinates x1, and then x2 and x3 were floating in the background because I can't draw them. And then I said that at each point in space-time we're going to erect this architecture, which we had developed very thoroughly before. It wasn't totally arbitrary, but it was going to be a vector space, its dual, all of the attendant tensor product spaces that might be constructed, and at each point it'll get its own. So if this was the point P, you'd have a vector space at P, a dual space at P, and then the tensor product spaces, and the basis of the vector space would be given by these differential operators as related to the coordinate system at the point P. And this of course led to the dual having similar, I guess I should label it with a little I or a mu. The dual would have a similar basis, and of course the dual basis was defined by mapping. The mapping will give you the delta function and all that stuff. But I stipulated that this will happen at every point in space-time. So every point in space-time will get its own structure like this. And then on top of all of that, we would give each of those structures a metric, Gij, and from there we were going to, the next place we would go is we would talk about curvature, and we would talk about the Einstein equation. So that's how we would have gone with the normal set of lectures. But now that we understand manifolds in this section, we are going to actually construct this logic more rigorously, because it is otherwise hand-waving. It is enough to get through the subject, by the way. What I've done in What is a Tensor is good enough if you accept this concept. But now the space-time will end up being a manifold, and these vector tangent spaces that we talked about at each point, we're going to actually build them out of our manifold architecture. So let's begin with that project. In order to begin, we will start with a manifold. And that manifold, we won't call it a space-time manifold, we won't call it 4 dimensions, we'll just call it, as we always have, X with its topology and an atlas. And on that manifold we will create a function, like we discussed in our last lecture, but this time the function will go to another manifold, but that's going to be a very specific manifold. It's going to be the real line. And so this is already Euclidean. It'll be the real line with the topology of the real line. And this being already Euclidean, I won't worry about creating charts on this line to a Euclidean manifold. This thing is already Euclidean. So we're going to spare ourselves a step. But here we can't spare ourselves a step. And we know that this thing, this being a manifold, it will have a chart. And that chart will go to RD. And well, it'll have an atlas, and this atlas will be exemplified by this one chart. I'll provide one chart, U1, gamma 1. And the question of the differentiability of this function, we learned from our last lecture, will be the function gamma 1 inverse composed with f. That is a function from RD to R. And therefore we can decide whether or not it is differentiable. So if it is, we can call that a smooth function if it's infinitely differentiable. And in the last diagram, of course, we would have had to include, to make it exact fit for the last diagram, we would have had to include, say, an open region here, V1 and phi 1, and bring it to another R, right? And then we would be interested in the differentiability test would be gamma 1 inverse with f with phi 1. But here phi 1 is just the identity on R. So by replacing phi 1 with the identity on R, because V1 could be, if we set V1 equal to R itself, which is fine because it needs just to be an open set, and we set phi 1 to be the identity at R, we basically are just moving R to R, and it is a manifold structure. It just has one chart. The whole atlas will just have one chart. I guess I would have to call that atlas B, right? This atlas would just have one chart, V1 phi 1, and that would be sufficient, and that one chart would plot everything over here, and then if I make it the identity mapping, it's just a trivial extension. So we're going to skip it all. And that the effect of skipping it all means we are dealing with the differentiability of this alone. All right, so with that in mind, so I will erase this to show that we are not using it anymore. Well, I better just redraw the line. And now I have a function, a simple function from the manifold. Well, F itself, by the way, is a function from the manifold to R. This guy, this composition, is a function from RD to R, and that's the one that we want to be C infinity. So we're going to call a function of F that is C infinity like this. F is an element of a set called C infinity on X, which means smooth functions on the manifold. Smooth functions on the manifold. And it's a large set. In fact, it's actually a vector space, because if I have two such functions, F and G, if they're both in C infinity on X, I can define an addition property. If I do this as pointwise addition, right? Pointwise addition. And I can make it a real vector space by defining a multiplication property by regular old multiplication by real numbers. So I have an addition property, a multiplication property. These two things, it's not too hard to show, are closed, and therefore C infinity X is actually a vector space given these two properties. Important thing to notice that that's the case. All right. So now we have this function. So what else do we need to start to get ourselves on to this subject of vector spaces? Well, we need the idea of a curve. We already have a curve. We already have the idea of a curve. We understand how that works. That is a function which I'll call Sigh. And Sigh is a function from the real line to the manifold. And the parameter for this function I'll call t. Suggestive of time, because ultimately I think that is really the way to think about it. In a lot of books, when they talk about this, they use Greek letters, so it would be lambda or phi would be the parameter of this function, but we're going to use t for whatever reason. So if there's a point, if there's a point on this real line, and call that point t0, then the point up here is psi t0, like that. And of course, because this is a manifold, right, a differentiable manifold, we know that this gets plotted into RD through some chart. And the curve itself, all of phi, might be represented by, well, let me do it in a different color. All of phi might be represented by this curve here, and that curve will end up in RD here through the action of a map, say gamma. Right? So that's how the curve works. Now, so gamma is a function, this is RD. So gamma will take this to RD, but what's interesting now is we have two things. First of all, we have our differentiable manifold, right? That's a given. And I now have stipulated the existence of a function, actually a whole class of functions, a whole class of C infinity functions, one of which I'll call F. And F takes that manifold to the real line. And this is, F is not a diffeomorphism. It is just a function from the manifold to the real line. And so now I can start thinking about something that might look like a derivative, right? Because what I can imagine is I can imagine the inverse function, which I shouldn't call a function, the inverse mapping, because it's not a function, right? Because if I take a point on the line and I run it through f inverse, I'm going to end up with a collection of points here in the manifold that satisfy that this point inverse maps to a whole variety of points, right? It's not really a function because it's one to many, right? It's one point here to many points here. And if I do this for different points, I'll actually develop, in some sense, a bunch of labels over here that are essentially contours, right? And I can even get them closer. So it'd be some sort of contouring over there where all of the points colored in blue are the locus of the points that are labeled with the real value of the function f. And so now, the reason that this gives me some sense of a derivative, perhaps, is I can imagine moving along this curve phi, and I can use that curve to sort of sense how the value of f is changing on the manifold. And of course, when I speak of the value of f, I'm talking about this value here. But what I've done by projecting back the inverse mapping is I get this idea that there's this possible notion of the curve crossing these equa f contours and getting a sense of how fast that curve is moving past values of f. And that is sort of a derivative type notion. I mean, it's certainly, as I change the question I'm asking is, as I move along this curve, how fast am I changing values here? So I could say, if I'm moving t, how fast do I move in f? So I can think of a concept that might look like df dt. Now, actually, I don't even have to think of partial derivatives, right? Because I only have a function of one variable to one variable. So I could actually think of df dt. Now, let's not get confused with these df's as the differentials or as the forms that we talked about in previous lectures. I haven't mentioned anything else. Think of this in terms of regular old calculus, right? So this thing could actually be meaningful in some weird way. There are some problems, though. The first problem is, whatever this guy is, in normal calculus, we kind of think of the derivative of f with respect to t as a simple and obvious function. The problem now is whatever this derivative is, it's going to be highly dependent on the curve. Because clearly this curve phi, as it explores f, is going to be totally different exploration than, say, that curve, which I might call that green curve from its own r, right? It's got its own function, and I won't call that psi, I'll call that one phi, for example. A lot of Greek letters here, right? But gamma is the chart map, right? So gamma is the chart map. But these other Greek letters are actually functions, or these other Greek letters are curves, right? So let's keep that clear by writing it down, I guess. But clearly, if I use this curve to kind of create some structure like this, the result is going to be totally different than if I use this curve to create some structure like this. So this structure, if we're going to do it this way, is going to be dependent on the curve we choose. And that's actually an important point. But regardless, if we do choose a curve, what is the function we're interested in? Well, if we say we stuck with f, well, we're interested in the function that goes from here to here, because we can actually take a derivative of such a function. We can take a derivative with respect to t, because the independent variable will be t, and the dependent variable will be whatever lands over here. We'll call that'll be the df. So that function is going to be psi inverse. Well, no, actually it's not psi inverse, I'm sorry. It's just psi composed with f. Because psi, remember now, is going this way, right? I'm confusing it with the chart maps. The chart maps go from the manifold to RD. But in curves, the mapping goes from the real numbers in. So it's just psi followed by f. And that is a function from R to R. And we can just take the derivative of that. So I'm now interested in this thing. I'm interested in phi psi composed with f derivative, and its independent variables t. I'm now using parentheses around this. This is the name of a function, right? This thing here is the name of a function. To kind of be able to make this prime look like it's going on the whole name, I'm kind of throwing down these parentheses here. But understand, this whole thing here, this is the name of a function, and I'm saying I'm taking its derivative. The independent variable is f, so I'm taking that derivative with the independent variable is t, so I'm taking that derivative with respect to t. That function here is what I'm going to call, perhaps I would call df dt. The problem with calling it df dt, though, I'll put this little tentatively. If I were to call that df dt, I kind of have a notational problem, because f is actually a function from the manifold to R, right? It's not a function from the real numbers to R. This is the real numbers to R, right? Because I have to have that composition in there. So when I write it like this, it actually doesn't make any sense, because this function's domain does not include t. It's x. So in some sense, this is a shorthand, where when you see this kind of notation, you have to realize what you're actually talking about is this thing here. And that's not too hard to do. You could just redefine it, right? Because if f composed with psi, well, what is that really? Of t. What is that really? Well, that's f of psi of t. Well, I can just redefine that as, say, f tilde of t. In which case, I could do this and put the tilde over here, and now everything is fine, because I've kind of redefined a function f tilde that is this, and essentially f tilde is that thing, right? And sometimes you'll see some books do that. A lot of books just jump into this notation, and they're counting on you to understand that when you see the f in this context, you're actually thinking about this full function here, not just that function there. But since we're dealing with manifolds, and that's what our lecture's about, we've got to be a little more detailed. So we're going to keep this notation, all right? Okay, so now with that in mind, we'll go to the next step. And the next step, well, we'll clean up this chart a little bit, and I'll redraw it quite quickly, but the chart is very important, and it doesn't hurt to do it over and over again. This is t. I'll call that particular point t sub 0, but the parameter is t, and this will be psi of t, and we'll talk about now just one of these curves, right? And of course we have gamma, and the curve lands in RD, and we also have f. So now, the function we're interested in is, and this goes to R, right? The function we're interested in is psi composed with f. And now I want to start talking about a new kind of object, yet another kind of object. It's all predicated on the existence of what we already have. We have an f, we have our differentiable manifold, we have a curve. So the two new things we have are this curve and this function f. And through those two things, we're going to create this notion of a derivative. And so what I want to think about is some object, I'll call it scripty v. That object is going to be a map. Everything's maps in this business, as you can tell. And it's a map from C infinity on X, where X is our manifold, right, to the real numbers. Now, we already kind of know that we have something that we think is going to be close to what we need. We've created this object here. Now notice, how does this work? Well, you can think of it as it takes a function f, and you construct this derivative, and if you plugged in a value of t, you would get a real number. So for example, if I put in t0, then this ultimately, this thing would be a real number. So it looks like we have everything we need. We have a device that takes a function and gives a real number, but what's interesting is the device requires a curve, and it requires a point on that curve. So in order to make such a device, I would have to provide it a curve, so I'll do that by giving it a subscript of the curve itself, and a point. And I'll call that point t sub 0. So now I'm dealing with this question of subscripted subscripts. So maybe we'll adjust that later. I tend to like to get away from it. I don't mind it if you're using, say, a typesetting program like LaTeX. I don't mind subscripted subscripts, but writing it can be a bit of a chore. But for right now, if I have this object, which is clearly defined by the curve and defined by the point, it will be a map that takes functions and gives you real numbers, and that's what this is. So I want to know what type of object would this be? And I would write its operation the following way. I'd write v of psi at t0 operates on a function of f, right? And that operation is going to look like this. It's going to be compose that function with the curve, take its derivative, and evaluate it at t0. Right? This here defines this object v. And I'm going to call that object v for now the velocity. Right? It's a type of velocity. Right? It's not velocity through space-time. I don't want you to make too big a deal out of it, but it is the velocity essentially of this curve through this inverse function's contour fields, right? So this inverse function has these contours here. The velocity of this curve as relative to the contours of this function, that's what I mean by velocity here. So if I had something I could call the velocity, I could feed it a function, and I will end up with a real number. All right? So let me write that down again a little bit clearer and separately. The velocity of this function, the velocity of that curve at that point operates on a function, and the way it operates is you compose the curve with the function, which gives you a function of t, right? That thing is going to be a function of t. You take its derivative, with respect to t, and you evaluate it. Well, wait a minute, what am I doing here? You take its derivative with respect to t, and you evaluate it at a single point, t0, right? And that is the map we seek. So this here is the map, and this is how the map is defined. And that thing is called the velocity. All right, so now that we have all that down, we're going to think about a bigger problem. One of the things that we're faced with when we consider this notion of a velocity is the inevitable fact that it needs a curve. So if I have my real numbers here and my parameter t, and I say I pick t0 and I create this curve psi, and psi runs through the space and hits p at psi of t0, there's absolutely nothing stopping me from building a whole different curve. We could say it's centered at t1 and call it phi, and phi goes through p, which equals phi of t1. And I can do this again. I can make another curve, sigma, which goes, say, from t2, and it also goes through this point. And sigma t2 is at p. So I have three curves. And it's fine. You can have a lot of curves in this kind of work, right? There's no stopping you from choosing all these curves. The point is that each of those curves comes with its own so-called velocity at p. So the velocity of psi at p is something we can define, and we define it as, remember we have this arbitrary function f, which goes to the real numbers, as, well, the velocity of psi at p, let me get this correct, composed with an arbitrary function f, where f is an element of the smooth functions on the manifold, where our manifolds are always x, right? X, tx with an atlas, a differentiable manifold. And we know that this is going to be f compose psi prime at t0, t0. Let me make my t a little clearer. And then, of course, we're going to have a velocity associated with phi at the point P, which will act on the same function f and give you a totally different answer, right, at T1. And then a velocity sigma at P, which would operate at f, and yet again give you a totally different answer at T2. So we have this nice notion of how to create a map, how to create a map between C infinity of x and the real numbers, because this will be a real number, right? This is a derivative with respect to this parameter t evaluated at t0. So that's going to be a real number. And all three of these are going to give real numbers. And they're all going to give different real numbers acting even on the same function f, because each curve explores f in a totally different way. So just because we have a manifold and we can make curves and we can create these velocities for each curve doesn't mean we've really constructed anything that's a useful derivative of a function, for example, because the function will have an infinite number of different so-called derivatives. And that's, of course, exactly what, I mean, this makes total sense, right? Every curve is going to operate on this function and produce a different real number. Some curves may produce the same real number, by the way. Some curves may explore f in a very similar way, at the point P at least. But there'll be an infinite level of variety of these curves. So are any of them special? And the answer is no, none of them are special. But we have this usual workaround in this subject when we're dealing with things that are individually unique, but we want to treat them all without any favoritism. And what we do is we create a set. And we create a set, in this case, a set of velocities. And the set is designed so that as long as gamma is a curve, I'm going to consider the set of every possible velocity associated with every possible curve at the point P. So this set is assigned the point P, and it's filled with the velocities of every curve that exists, period. All the possible curves that can exist that I'm going to create a velocity for. And this now is a set of maps. It's a set of all possible, well, it's a set of maps from C infinity to the real numbers. And the maps are all defined this way. Well, the maps are all defined as this way here, but the set of maps is all possible size, lambdas, sigmas, etc., etc., etc. So that is what I'm after. And that's a similar problem as how we solve the issue of the dual space. Remember, the dual space, if you followed along with the last lectures, was the set of all possible maps, because you can't just define one map, just like you can't just define one curve. You have no foundation, no reason to pick one curve. So you consider the set of all possible curves. Now, what's important about this is that I want to show that this set of all possible curves, I want to show that it's a vector space. And in order to show that it's a vector space, I have to show several things. I have to show that I can take an arbitrary curve, an arbitrary, not curve, an arbitrary map, plus a different arbitrary map, and the sum, the so-called sum, I have to define this sum, right? I have to define that sum in such a way that I know that there's another curve that goes through P whose velocity can be understood as the sum of these two velocities. And the way I'm going to do that is I'm going to say that this velocity operating on F plus this velocity operating on F are two real numbers. And I need to prove that there's another curve out there whose velocity operating on F is the sum of the real numbers. Because now, when I put an F in here, this addition becomes a real number plus a real number. That's real number addition. So the real number, I better find a map that's in this set whose real number answer is this sum, right? And then what I just do is I simply remove the F, and then what's left becomes the definition of the vector addition inside this set. So that I need to show. The other thing I need to show is that I can take a real number A is an element of the real numbers, and I can multiply it by an arbitrary vector in, see these are at point P, I erased my P, an arbitrary member of this so-called presumed vector space, but an arbitrary map that lies here, an arbitrary velocity associated with a curve, or a velocity associated with an arbitrary curve, any way of saying with a member of this set. And that result, I should be able to find another curve in this set that is associated with this. And again, that association is going to be this way. This curve with the scalar product with A has got to equal, and acting on a function f is going to give you the same real number as some other curve, sigma, whose velocity is acting on f. I have to prove that that exists also. What I'm going to do in these lectures is I'm going to spend some time and I'm going to prove the first one. I'm not going to worry about the second one. The second one is much easier than the first one. And I'm going to actually prove this first one. And you have to prove a few other things too. You have to show that there's a zero velocity. You have to show that every velocity has an opposite velocity, which would be multiplication by, say, -1. But I'm just going to spend the time and prove this, and I'm going to leave the others unproven. But if I can show those things, then I can show that this is a vector space. And if I can show that that's a vector space, then I've shown that at P, there's an entire vector space of velocities, one associated with every curve that goes through it. And then once I have that vector space, then I can ask all the questions like, what's the good basis for the vector space, and things like that. I'm not going to get that far today. It's already going to be a long lecture just to prove that you can do this. So I'm going to redraw it a little bit smoother now, and I'm going to try to do this abruptly off record. All right, so here it is. This is the basic setup, right? We have three different curves. The curve, the psi curve at t0 brings you to the point P. The phi curve at t1 brings you to the point P, and the sigma curve at t2 brings you to the point P. So this, all of them are have a spot on their curve. They all go through P, is a way to say it. And these curves all look, they're all supposed to be different curves. There's the psi curve. And the point is we're going to now study velocity at the point P associated with these two curves. And we're going to show that there exists a curve sigma that we can actually construct that will represent the sum of those two curves. And the way we're going to, what we're after is an expression like this. We're after an expression that says the velocity of the psi curve at P plus the velocity of the phi curve at P equals, that means there exists some sigma curve at P where you can say that the velocity of the sigma curve at P represents somehow the sum of the velocity of the psi curve and the phi curve. And you can do this for any curve, psi and phi. You can always construct this sigma. And the way we're going to do it is we're actually going to suggest a sigma. Based on psi, if we know this, and we know psi, and we know phi, we are going to actually offer up a sigma that will always be representative of this sum in one way or another. And we're going to see if we can figure that out and make this proof. This is the only proof I'm going to do here. I think it's important because it also it shows you how we're going to construct a vector space out of this object, right, where gamma is a map from R to X. But notice that we're starting, by the way, in a chart, right? I'm just going to do this on one chart, a chart U. U is an element of the chart atlas, and the overall set is X, but we're just focusing on one chart, and that chart has a chart map gamma. Now, in the end, this proof is not going to be dependent on what chart we choose, but we're kind of going to need that chart to wind our way through this proof. And the proof we're seeking is that such an addition property can be defined and is closed in the way we described it. All right, so the way we're going to begin here is I am going to write down theta. I'm going to write down, not theta, sigma. Sigma is going to be, I'm going to define sigma of t in the following way. It's going to equal this object, the inverse gamma function, the inverse of the chart mapping, applied to the chart mapping composed with psi, applied to the point, applied to the point, this is t, applied to the point t0 plus t, add to that the chart mapping applied to phi at the point t1 plus t, and subtract from that the chart mapping of psi applied to the point t0. All right, so this is kind of a weird structure, right? But this is a curve. And it's a curve because the dependent variable is t, right? Here's where t shows up and here's where t shows up. So we know the dependent variable is t, so that works out. And how about its domain and range? Well, this guy here is a map whose domain is the real numbers and its range is RD. Its range is RD. So there's a real number. So this thing here is an element of RD, right? Likewise, this thing here is an element of RD, and this thing here is also an element of RD. Well, this inverse element of gamma takes RD into the manifold, so this ultimately is a function from the real numbers to the manifold X. Specifically, I guess I should write to the real numbers to U, which is a subset of the manifold X, right? To the chart mapping U. And it's all good for this chart. So we've created a sigma. Now the question is it the right sigma? Is it the sigma that's going to make this logical and true? In fact, just to keep everything really clear, why don't we do one of these charts where all the maps are shown, right? We start with the real numbers. The real number, this map we've invented called sigma, right? And that takes us into U, and then U goes back to the real numbers through some function f that's unspecified. That's our element, where f is an element of the smooth functions on the manifold X. Likewise, U maps to RD through the chart mapping gamma, and that's because U and gamma are an element of the atlas, right? And ultimately the topological space is at the bottom of all this, right? The fact that it's I keep calling it topological space, the differentiable manifold is at the bottom of all this. So because this is a chart mapping, it takes us from U to RD. Okay, and then what? So what about this map? The map from the domain of the function of sigma to RD, which is basically saying, where does this curve plot out here, right? Out here. That would be starting with R and ending up in RD. So this guy here. Well, what is that? That's going to be gamma inverse. Well, if it starts here, it's going to be sigma gamma, right? So that thing is going to be, we act with sigma on the real numbers and then gamma on the point in the manifold, and we get the function sigma gamma. There's also this function, which would go from RD to R, and that is going to end up being, we're going to use gamma inverse to take us from RD back to the manifold. Gamma inverse takes us from RD back to the manifold. Then, of course, F is what takes us to R, so we compose that with F. So these are this is a nice little rubric to keep in mind of where all these functions go. And so this makes everything, I mean, you can look at it this way too. You can just sort of follow the lines here. From RD to R would be this way here, the last line. But we basically use this construction, and this tells us where all these functions go and belong. Okay, so now let's see if we can figure out, based on what we've done already, we've defined a function. Now I've just given you this function. It's a constructed function, and it's a claim. It's a claim that this thing is going to satisfy some sort of rule like this. And it's sort of backwards because I'm not explaining how we came about this. I'm just saying some guy who solved this problem came up with this function, and we're going to check that he's right. And basically this is checking the work of some other mathematician in a sense. But remember, that's part of the creative element of mathematics. I can establish this if a function like this exists. Well, one way is to construct a function, and somebody sat down and worked really hard and came up with this function. And now I just want to prove to you that this function does the trick. So one question we would ask about that function is, what is T1? I'm looking for what value of T1, or I guess it's T2, sorry. What value of T2 equals the point P, right? Well, I'm going to claim that sigma of 0 equals P. And so T2 equals 0. And how would that work? Well, if I put in 0 for t here, I get phi of t1. Well, phi of t1 is p, and this is the chart representative of p. So this whole thing here is the point p mapped into RD. Well, I inverse that, and what do I get? I get the point p. So this thing, when t equals 0, is p. How about this? Well, it's the same way, right? It's now it's just T0. It maps to point P. And what about this? Well, this is actually well, okay. So we got to get this actually straight. This thing here is a ordered pair of points that represents P. This is an ordered pair of points that represents P. So now, when I do this calculation, I get AB here and AB here. Those are two ordered pairs. Now in R2, if I add those two ordered pairs, I get 2A, 2B. And then, and this addition property is for R2. Because remember, these guys live in R2. So this is the addition property of R2. So now, what is this thing? Well, this is gamma operating, well, at T0, psi on T0 is P. Gamma is the representative in R2. So now I'm going to subtract an ordered pair. I'm going to subtract an AB. And ultimately, 2A, 2B minus AB equals AB, which is the matrix which is the coordinates of the point P in RD, right? AB. And now sitting out in front of this whole thing is this gamma inverse. So ultimately, this whole thing here, let me draw it correctly, is now gamma inverse of the ordered pair AB. Well, gamma inverse of the ordered pair of AB is P. So that's when this whole thing is evaluated at t equals 0. So now I can write that sigma of 0 is the point P, and likewise t2 equals 0. So that's interesting. So this definition here of sigma t has the nice property that at t equals 0, sigma equals the point P. All right, now that we have established this, and we have decided on a candidate sigma to work with, now we need to study, and I've cleared the screen a little bit, but now we need to study this, how the velocity of sigma at P looks. And the velocity of sigma at P, as we know, it's a map that takes C infinity functions and it operates in the following way. It's the function composed with the curve sigma, it's that derivative, and it's taken at the point, associated where sigma intersects, P, right, where sigma actually hits P. So it would be at the point sigma inverse of P, which is just a fancy way of writing f composed sigma, the derivative, at 0. Because we now know by construction, we've checked that sigma of 0 was P. And therefore, sigma inverse of P is 0, which is why we got that. So now we have to understand and we have to study this guy. This guy is the one that is, when we expose this, we're gonna take this, we're gonna work on this very hard, and ultimately we're gonna come up with something on the right-hand side that looks like the right-hand side is going to end up looking like V psi of P of F plus V phi of P of F. And from that, we're going to be able to conclude a rule for taking the sum of two of these velocities and getting a third. And once we have the sum, then we have a sum rule for the vector space. I'm going to prove the sum rule. I'm not going to prove the scalar rule because already this lesson is going to be really, really long. But then what we'll know is we'll know that these velocities, the velocities of all the curves that go through a point, form a vector space. So we're going to execute this proof right now. Okay, so before we begin here, let me point out this is not an easy proof. This is actually pretty subtle, and there's a lot of pieces into it, and the chances of me getting through this without any flaws the first time is pretty slim. But let's see what we got. This is the function that, this is the curve. This is the curve that we propose will enlighten us about how to add two vectors together, two of these velocities together. So the velocity associated with the curve psi and the velocity associated with the curve phi come together through this formula to produce another curve, sigma, which we claim will have a velocity that can be considered the sum of these two velocities. Now, when you look at this formula, you may think psi comes in asymmetrically, right? Why is psi favored over phi if we're considering something that involves the sum? And this thing would work exactly as well as if you replace this with phi. Because remember, all this needed was to subtract an ordered pair of the point P, the ordered pair associated with the point P, from twice the ordered pair associated with the point P. So if I had phi here, I would have sufficed and gotten the same thing. So it really doesn't matter whether we put phi or psi here. However, you do have to have this term and this term together. And this is the velocity that we're interested in. The velocity of this new curve at the point P acting on a function f, and it's defined through this, where the function composed with the curve, you take the derivative with respect to the parameter, which is t, and we evaluate it at the point where this curve actually intersects P, which we've discovered was the point 0. So this is the thing that we're kind of interested in. So we have to understand, too, that this is all with respect to a certain chart. Oops, I've increased the thickness of my, my line here. This is all, so if that chart is U, the chart map is gamma. And that, of course, takes everything into RD, right? And then the curve, of course, is going from R, so this curve sigma, where we have the sigma of T, and that lands here in U. So we got the curve in U and the curve coordinate representative in RD. So the first thing we're going to actually do here is we're going to complicate the matter by inserting the chart map and its inverse into this formula. And we have to understand that this chart mapping and its inverse doesn't change anything about this. We can always throw in something times its inverse. And that's done in all kinds of proofs throughout physics and math to squeeze in something times its inverse to create something that's actually looks more complicated but is a big seller in simplifying things. But now we have the composition of 1, 2, 3, 4 functions. Just to make sure we understand what we're talking about, we're talking about a function f that's operating on an argument. And that argument is what's returned by inverse of gamma, which is in itself operating on gamma, which is operating on sigma, which has a parameter t. So let's see if I got all my parentheses right here. I think I need one more. So this is a composition of functions, and in normal calculus it looks like this. But in the end, it's a real number, a. Well, actually, let me make the real number w. And so this function can be treated with a chain rule, right? And we're going to have to learn how to use a chain rule on this function in a moment. But that is what this thing means, right? And t, well, this thing almost means that. If you substituted 0 for t, then you would literally get this. If you replace this 0 with a t, then you would get that. So that's what we basically just jammed in these two extra functions inside this definition of our velocity. All right, so now, once we've done that, now we are going to break it up. We're going to break it up into the following form. I'm going to look at f composed with gamma inverse, and I'm going to treat that as a single function, which it is. That's the name of a function. And I'm going to compose that function with gamma composed with sigma. And that will operate on 0. These parentheses are serving weird purposes. What I'm actually going to do is I'm going to take, when we get to the point where it operates on something, oh, by the way, there's a derivative sign up here, right? I'm going to put it in brackets. And this whole thing here is the name of the function, and I'm taking its derivative. The brackets are now meant to symbolize that's sort of the value it's operating on, right? That's the argument. I'm going to put the argument in brackets. In fact, why don't I go back and do it up here too? That'll be a little clearer, if you can see, because we use the parentheses now to separate function names a lot. But here I'm using brackets to separate the function names. So, but the reason I need the brackets here is because I want to somehow indicate I'm taking the derivative of the composition. If I left out the brackets and put the derivative here, you would think I'm taking the derivative of this and composing it with that. But I'm taking the full composition and then its derivative. Okay, so what are these functions? So let's have a quick look at what these things are. What is sigma composed with gamma? Well, gamma is the chart mapping. So sigma is the function from the real numbers into the manifold. So this thing here is essentially this line here. It's the chart representative of the curve in the manifold. That's what this is. So what is ultimately what that has got to be is that's an element of RD, which means it is an ordered pair alpha 1 ... to alpha d, where I've gone back to going from 1 to d. So on my index. So this thing here is an ordered pair, is an ordered D-tuple that lives in RD. And what is this thing? Well, this thing obviously eats a D-tuple and then returns, after it eats the D-tuple, it returns a point in the manifold, and then the function f takes that point in the manifold and gives me something in R. Right? So this guy here is a function, so I should write f operating on gamma inverse is an element of R, and it's a function from RD to R, right? So this is just a single number. So now what do I have when I look at the whole thing inside the braces, right? Inside the braces. When I look at the whole thing, I see a function from RD to R followed by a function from R to RD. So this whole thing here is ultimately a function from RD to RD. So that's the way to sort of peel apart this stuff. When you read these proofs in books, you're going to have to sit down and really think about the domain and ranges of everything. So I'm looking for the derivative of a function from d-dimensional Euclidean space to d-dimensional Euclidean space. All right, so how does that work? Well, now we have to go back to our multivariable calculus. And let me erase this so I can keep this explanation on the same screen here. I'm going to remind you of a formula for multivariable calculus that kind of goes like this. If G, I'm going to change letters here, if G is a function of x1, x2 through, say, xn, and xi is a function of u1, u2 to um, then if I write w equals g of x1, x2 to xn, I can ask the question, what is w, the derivative of w with respect to one of the u's, the ith entry in the u list? And I can ask that question. And the answer to that question in multivariable calculus is dw dui equals del g del xj del xj del ui. Let's see if I got that right. The i's should match here. This is an Einstein sum, so it's a summation of g and I. Yes, so this all works fine. So this is the multivariable calculus expression for how to take the derivative of a composition, a multivariable composition. And where g is a function of these x's, but x's are in turn functions of these u's. So when I take the derivative of g, I'm taking it with respect to the jth entry in this list. And when I take the derivative of x here, I'm doing it with the ith entry in this list. And that's how I get the partial derivative of the overall function with respect to the ith entry of the u d-tuple, or m-tuple in this case. So this is sort of what I have here, right? This guy is a function that's looking for a d-tuple in RD, and this guy is a function as well that will produce a d-tuple in RD. So I can use this chain rule to take this overall derivative, and that's what I'm going to do. All right, so I've repeated everything here, and as a word of warning, the proof is not easy. And you can actually, if you just trust that this is a vector space, that we've got a vector space going on, you don't need to watch this. But I'm going to kind of go through the proof just to systematically do one demonstration. And also it really exercises our understanding of these curves and all this notation and this multivariable calculus. It's worth doing, but it will make this lesson unusually long. But so to begin, we need to remember first about how gamma is defined. Gamma of p, remember, was a bunch of ordered pairs, or not ordered pairs, bunch of coordinate functions, coordinate functions that produced a d-tuple. So I can totally logically speak about the ith component of gamma, because what it is I'm just selecting the coordinate function, the appropriate coordinate function out of this d-tuple. We're going to need that fact in order to construct and to utilize this fact here. Now, you remember I squeezed this thing in. What we're going to do is we're going to execute this chain rule on this object. But this object has now got two functions. So we're going to actually break this object up already into something like this. F compose with the chart map inverse composed with the chart map on sigma. We're taking the derivative of that at the point 0. So this, there's really been nothing, there's no difference between this and this. But I want to think about this as one function and this as another function. And I'm interested in this derivative. Well, I can literally use the chain rule, the multivariable chain rule, to calculate this derivative. And that's what I'm going to do. I'm going to go that this thing equals the derivative with respect to the ith entry of f gamma inverse. Now this is a function that I have to multiply by another function, so it needs a value. And the value is, of course, going to be the value delivered to it by the function with which it's composed. I'll talk about that more in a second. But this thing here, this idea here, is this part here. Right? This is g, y, evaluated at y of u. Right? So it's got to be evaluated at a point y of u. All of this, this presumption is that we're evaluating something at a point. So if I evaluate y at a certain value of u, I've got to evaluate g at a certain value of y, and w gets evaluated ultimately at a certain value of u. This is the certain value of y, which we would have evaluated g at. I'll do a little tidy example in a moment to show why that makes a lot of sense. And then this guy over here is gamma composed sigma, the ith component, right? Because we're talking about the ith component here, or the jth component there. I'm summing over I over here for some reason. Then why don't I change that now so it kind of matches. We take the derivative with respect to the jth entry, take the jth component's derivative, evaluate it at 0. So just to be clear where these evaluation points come in, just think of, let me think, think of if f of t equals t squared and g of x equals, say, x cubed, something like that, then I could ask for f of g of x. And I could also ask for f of g of the value 1, right? So if I ask for f of g of x, I'm going to just use the chain rule, right? Well, I can compose the function straight up, and I can get x to the 6th, and then then that becomes what, 6x to the 5th. I could also do this as x cubed squared, and now to do that I have to go 2x cubed times 3x squared, which equals 6x to the fifth, right? That's using sort of the chain rule in a admittedly absurd way with this example, but that would be using the chain rule. But notice what you actually did here was you said, I took the derivative 2t and I evaluated it at x cubed, and then I took the derivative of x cubed, which was 3x squared, and I evaluated that at x, essentially, and I ended up with 6x to the fifth. Had I evaluated at 1, I would have ended up with 2t evaluated at x cubed, and then x would have been 3, and then I would have had to do 2t evaluated at 3 cubed, right, which would have been 27 times 2 or something like that. So the point is these substitutions here, these substitutions here are implicit in the chain rule. We just get so used to doing it different ways, but they're implicit there. And that's what this is here. This x cubed sort of corresponds with the composition of this function being composed with this function. Just like x squared was composed with x cubed, f compose gamma inverse is being composed with gamma dot sigma. So I need gamma dot sigma evaluated at 0, which is ultimately what happened here. So the point is that you've seen this before. It's just we don't typically formally do it when we're doing normal chain rules, but it's there, and that's why it shows up up here as well. So it's this function evaluated here multiplied by this function evaluated here and summed, and that summation is driven by the multivariable chain rule. So once we have this now, we have two things to work with. We've got this object and we've got this object. So let's work on this object first. The map function, or the jth component of the map function, evaluated at 0 and its derivative. Well, we're now going to substitute, our sigma, this sigma, our proposed sigma, we're going to substitute it in here, and we're going to see what happens. All right, so that substitution is going to look like this. It's going to be, I guess I'll put everything in braces here. It's going to be gamma composed with sigma. Sigma starts with a gamma inverse, right, which is a little bit lost on the screen there, but it starts with this gamma inverse here, which ends up right there. This sigma here comes from that sigma there. Then that is composed with, now this gamma inverse is actually composed with this whole thing, right? Because it's gamma inverse of this whole thing, which is just another way of saying composed. So I could have put this gamma inverse in front of each one of these with a compose, and I can put it here. So that's where this compose is coming from. It's this implicit function of, or it's this implied, no, not even applied, this explicitly shown functional relationship of gamma inverse with all of this. That's what that composition is. So, but I get another gamma, right? Get another gamma, and then I get a Sigh, which I've been running in red, and that will operate on T0 plus T. And then I add to that the same stuff, but now it is phi, and it's of T1 plus T. And then from that I subtract this last term, which will look the same as gamma compose gamma inverse, compose gamma, compose psi of just T0. And then I take the bracket of this, I'm bracketing this whole thing, I take the jth component derivative acting on 0. So that's the substitution, right? That's the substitution of our proposed let me go here. Sigma of t. That's the substitution of our proposed sigma of t into this part of the multivariable chain rule. So now I can actually kind of work on this a little bit, right? First of all, I notice right away I'm taking the derivative, and that derivative is with respect to the variable t, because all these compositions are of curves. And so the domain of this function is the domain of these curves. That domain of those curves is t. That's the parameter. The parameter is t. But this thing isn't even a function of t. It's not even a function of t. So right away I know that I can eliminate this term altogether, because when its derivative is taken with t, it goes away. The other two, their derivatives with t remains. What's nice, though, is that these pairings of gamma and gamma inverse go away because they're inverses of each other. So those go away right away, and I'm left with these things. So what am I ultimately left with? Well, I'm left with these things, and the derivative of those things, and then evaluated at t equals 0. So what am I ultimately left with? Let's see. I'm ultimately left with gamma composed with, I'm not going to go red anymore, psi of t0 plus t plus gamma composed with phi t1 plus t, right? The ith component derivative evaluated at 0. So now the sum of a derivative of a sum is the sum of the derivatives. So I can call that gamma of psi, the ith component derivative evaluated at t0, because t is now substituted for 0. And that is the gamma composed with phi, the ith component derivative evaluated at t1. Phew. Okay, so what are those things? Well, the first, these maps in here, that's the ith component of the curve's chart representative. So when I say the curve's chart representative, I kind of go back to this picture, right? I've got the real numbers, I've got t, and then this graphs some kind of line in the manifold, which is then graphed into RD, and this thing here is the chart representative, and that is the chart mapping done after phi, right? So this guy here is the chart representative of phi. This guy here is the chart representative of, this guy is the chart representative of psi. This guy is the chart representative of phi, the ith component. When I talk about that, the derivative is, of course, respect to t. So this is a derivative with respect to t, evaluated at t0, and the derivative of respect to t evaluated at t1. So we have a very good understanding of what that is. Now we need to finish up, right? We need to, remember, we're working on this whole expression, and this part here is just the second part. I've got to multiply it by this guy here. So before I do that, let's take a look at where it's being evaluated. It's being evaluated at the chart representative, or the chart mapping, acting on sigma of 0. But we know what sigma of 0 is. Sigma of 0 is the point P, right? Because for the sigma function, it turned out 0 maps to the point P for sigma, not for psi. For psi 1, I've got to go to T1, and for psi, I've got to go to T1, and for phi, I've got to go to T2. But for sigma, by the way I've designed sigma, right? The way sigma was designed, it was already known. It was a foregone, totally known thing that psi of 0 was P. So right away, when I start working with this, I'm looking at the chart representative of P. So, so how am I going to write all that down? Well, what I'll do is now I want to I want to multiply this, which is really this, by that. So I'll do that, I guess. I guess I'll do that right over here next to it so I can see everything. So so it's going to be two terms, right? It's going to be the derivative with respect to the ith entry of the D tuple evaluated at gamma of p, and that is going to be multiplied by the first term here, which is times gamma, the chart representative of psi, the ith component derivative, evaluated at t0, and that's going to be plus the ith, the derivative with respect to the ith component evaluated at gamma p, which is the same thing as above, and it's going to be the chart representative of the other mapping, evaluated at t1. And this sum here, that is equal to this guy here, and remember that was ultimately traceable to the action of the velocity on an arbitrary function f associated with the curve sigma, right? So this ultimately equals, this ultimately equals the velocity of the curve sigma at p operating on f. Okay, well that's really good. So now we still haven't gotten it doesn't look like we've gotten very far in proving that this is somehow the sum of the velocities of the curve psi and phi. So we have to look at these things very carefully, and when we look at this, we need to think about the chain rule again, because the chain rule, and I'll just sort of write down that other chain rule, dui equals, remember it was dg dyj dyj dui, right? What we now have is, instead of trying to find the derivative of a function, which is what w is, because remember w was equal to g of all these y's, and the y's were all functions of the u's, right? So instead of trying to find the derivative of a function, we're going to take the sum of derivatives of functions that are being multiplied together in just the right way to go backwards. We're going to go this way, from here to here, because that's what we have here, right? That's what we've got. We've got a summation that looks exactly like the right-hand side of the chain rule. Likewise here, and they're both identical. The only difference between the two is psi appearing here and phi appearing there. In fact, I can highlight that by going back to my color convention like this. So using the chain rule in reverse, where do we land? Well, let's see. We land this first term here, right? This chain rule, it's going to be f composed psi evaluated at t0. So this thing's going to be equal to f compose psi prime evaluated at t0, and the other one is going to be f compose phi prime evaluated at t1. But, well, what is that though? But that's the definition. That's the definition of v psi at p acting on a function f plus v phi at p acting on a function f. And it already, we know by construction that this thing is v sigma at the point P acting on a function f. So through this choice of sigma and understanding that f is arbitrary, f is any element of C infinity on our manifold, now I have a way of defining that this is z psi of P plus v phi of P equals v sigma of P. Wow. That was a long proof. Notice the one important thing about this, by the way, is these charts. If you look at the chart mappings, they're gone in the final answer. In the final answer, when you invert this chain rule, the chart actually goes away. And that's really important because nothing can depend on the chart you choose, right? But we needed the chart to kind of get here because we needed that chart to do this step here that allowed us to sort of squeeze through with the chain rule. But this would work for any chart. Any chart you use, you're going to be able to define these velocity vectors. The reason you can use so many different charts is that it's an artifact of the fact that there are many curves through a point which have the same velocities, essentially. So you can pick a chart, you can pick all these different charts, and they'll all have, all the charts will end up in RD looking different, right? The chart representatives in RD of all these curves will look different, but they're all going to yield the same velocity. It has to do with that redundancy, which is why it's okay to use the chart, and the chart goes away in the end. All right, well, that was kind of a long lesson. But ultimately, what we have shown here is that for any point inside our tangent space, or inside our manifold, our differentiable structure, our differentiable manifold, we can set up this collection of vectors, v gamma, at that point, where gamma is a function, where gamma is a curve from R to the manifold. And that is a vector space. So the space of all of these guys, where they're defined through this key definition, this key definition, that object acting on a function, acting on a member of C infinity of the manifold, is given by the function composed with the curve, its derivative, acting at the point gamma of P, right? So, or at the point, if the curve is gamma. So this is an operation, this is an element of a vector space because it obeys all the rules. I didn't prove the scalar rule. It's easier than the other proof we did. We did the hard proof. The scalar proof is easy, but now we're really confident that this guy is a vector space, and this vector space is defined by all this infinity of curves that can go through a point P. And it provides us, each one of those curves at that point provides us with this beast that takes functions on the manifold, and gives us real numbers in return. All right, so that is the tangent space. And our next lecture is we're going to flesh out some of the utility of the tangent space.